So at this point, we are now going to start talking about integer exponents. Remember that an integer is what we call complete number. It's positives or negatives, including 0, but it's not a fractional number. It's like -2, -3, and so on. We know that when you have a number such as 2 and you have an exponent of 3, 2 is considered the base, 3 is considered the exponent, and what this is telling you you're doing is you are repeating the multiplication of 2 3 times. Pretty straightforward. But when we have things such as negative exponents, what really we are trying to remember is that a negative exponent is another way of saying you're a fraction. So if I had something like 2 to the power of -3, what this is saying is you are really dividing 2 3 times, because a negative exponent is like an inverse. So if you're dividing, we're thinking in terms of a fraction. So instead of 2 multiplied by itself 3 times, this is really 1/2 multiplied by itself 3 times. And the other way of thinking of it is that a negative exponent is basically telling you that you're a fraction and that you belong in the denominator. So if you were to look at it in that way, you could say that it's really 2 to the 3, but in the denominator, which will give you the same value of 1/8. Similarly, when we have things that are exponents of 0, we have to understand what that really means. So let's say that I had 2 to the power of 0. What this is showing is something that would look kind of like this. It's kind of like if I said to you, you have 2 to the 4 over 2 to the 4, where in reality, what has happened is that if you have 4 2's being multiplied in the numerator and 4 2's being multiplied in the denominator, this basically is going to create it so that each 2 is dividing by itself and you get 1. Or if you think of it this way, all of the 2's divide away and you're left with 0 2's. So 2 to the power of 0 is the same thing as 1. And this little rule can hold true for any number to the power of 0 is really equal to the value of 1. And we did use this last year. We went over a couple of things on that. So remember that a 0 exponent is basically a non-zero number that's raised to the power of 0 will always give you 1. And a negative exponent is anything to a negative exponent is really 1 divided by that number raised to the opposite. So basically you put it in the denominator and make it positive. So these are the rules, just as a quick reminder. Anything to the power of 0 will always equal 1. So for example, 2,357 to the 0 equals 1. When you're multiplying variables with the same base, you add their exponents, such that 2 to the 3rd times 2 to the 5th is 2 to the 8th. When you're raising a power to a power, you multiply the exponents, such that 2 to the 3 to the power of 5, you're raising it, so it's 2 to the 15. When you're dividing variables with the same base, you subtract their exponents, such that it's x to the a minus b. So if you had 2 to the 5 over 2 to the 3, it's really 2 to the 5 minus 3, which is 2. And 2 to the 3 over 2 to the 5 is 2 to the 3 minus 5, which is -2. A fraction is really a negative exponential expression. So x to the power of -a is really 1 over x to the a. So that 1 over 2 to the 3 is the same as 2 to the -3. And if you have a negative exponent in the denominator, it really comes up to the positive. We'll go over the roots in a little while. Let's look at this here as an example. The diameter for the Model A Ford piston could vary by at most 10 to the -3rd of an inch. Simplify this expression. Well, 10 to the -3rd, a negative exponent means you are a fraction. So 10 to the power of -3 is really the same thing as 1 over 10 to the power of +3, which is equivalent to 1/1000th. So if I was going to explain the reason to why anything to the 0 is equal to 1, it would look like this. when you have a fraction, we know it's a division problem. So if I had something like, and I'm going to use numbers first before we use letters. If I had something like 2 to the power of 4 divided by 2 to the power of 4, I know mathematically, because these are numbers, that I could actually do the math. I could actually punch in my calculator or multiply 2 times itself 4 times. And when I do the math, I get that it equals 16. Now I do the same thing to the denominator. I expand it out, and I get that he also is equal to 16 because it's the same expression. 16 over 16 is actually equal to 1 whole, right? Now there's also a rule that says that when you are dividing and multiplying, such as I am up here, I'm multiplying and dividing, you're allowed to divide before you multiply because there's no addition or anything that's getting it out of order of operations. So if I go to divide, I am allowed to divide away the 2's. For every 2 over 2, I actually get 1 whole. So this is equal to 1 whole, correct? This is equal to 1 whole. So is this, and so is this. And together they all multiply to give me 1. Additionally, the mathematicians discovered that because of the fact that you are allowed to divide away things that are on top with things that are on the bottom, the rule that they could say, the mathematical rule, says, well, when you're dividing items that have the same exact base, because of all of the math that comes into that, what you really are allowed to do is you're allowed to take that 2, because it's the same 2, and you go 4 minus 4. And that gives you 2 to the 0, because all of the 2's divided away. You're not left with any 2's whatsoever, are you? Do you have any 2's left up here at all when they all divide away? No. You have 0 2's, but the value is still 1. So they made that circular statement. If anything divides away with itself to give you 1, and you have no more of those items you had left, it means that you have 0 of those items, but the actual numerical value is actually 1. Let me show you with letters. This is one of those things that with letters, it might even explain even better. If I had x to the 4 over x to the 4, I don't know what x is equal to. But I do know that I'm allowed to expand out both of those to the multiplication problems that they are. Correct? Now, if I divide away my x's, this x is gone. This x is gone, this x is gone, and this x is gone. I have no more x's because they all divided into themselves. So how many x's do I have? I have 0 x's. But what is that value? Well, anything divided by its same exact self is equal to 1. So therefore, if you have nothing of an item left in your fraction, you actually have the value of 1 left. Because it doesn't matter what x is equal to. If it was equal to 1 billion, 1 billion to the power of 4 divided by 1 billion to the power of 4 is going to give you 1, because anything divided by itself is 1. Look at this one. And again, this should all be a little bit of a review, but if I have 2 to the power of negative 3, and I want to simplify it, you always want to make it a positive exponent. That means that the 2 to the 3 should go in the bottom, and now I'm under 1, so 1 over 2 to the 3. So that gives you 1 over 8. Anything to the 0 is equal to 1. This expression, got to pay close attention to it because it has a negative exponent and a negative number. You are raising negative 3, the entire negative 3 to the power of negative 4. So that means that you keep it in parentheses. That whole negative 3 is now a positive 4, and it's a fraction. So that when you figure this out, you're going to get 1 over, well, negative 3 times itself 4 times is going to give you a positive. 9 times 9 is 81. As opposed to this one. With this question, the 3, just the 3, is being raised. So this is really negative, and then 3 to the negative 4 becomes 3 to the 4 with a 1 in the numerator. So once more, the 3 is the one that's being raised to the negative 4, and the negative is just straight out in front because he stays negative. So that gives you negative 1 over 3 to the 4 is 81. So pay close attention to the difference between when you have negative 4, like you do up above, as the exponent of the entire parentheses, and in this case, the negative 4 is actually the exponent of just the 3, right there. Now, when you're evaluating, so look very closely at this one, you're evaluating, you're putting in for x, you're putting 2 in. So this is really x, which is 2, to the power of negative 1, which is equal to 1 over 2 to the positive 1, which is just 1 over 2. Okay, let's look at the next one.
Wait, how do you say that?
Polynomials. All right, you guys try this one. Try to evaluate this one.
What? Kind of doing a little space.
So if you think about what we're doing, when you are evaluating, you're plugging the values in. When you go to plug it in, it's really a to the power of 0 times b to the power of negative 3.
Isn't this the thing where
Then you, if they're the same variable, you add the exponents. You're right, we're going to get there in a minute. But plug 8 in for a, plug negative 2 in for b, and then you do exponents first because that's order of ops. 8 to the power of 0. Well, anything to the 0 is equal to?
0.
Anything to the 0 is equal to 1. Multiplied by, now I have to actually change that. It's the entire negative 2 being raised to the power of negative 3. So I'm going to relocate that negative 2 and put him in the denominator. Now his exponent is positive, and he's a fraction. 1 times anything is that same thing. This is really equal to 1 over...
No, positive, yeah, negative 8.
And then, negative 2 times negative 2 times negative 2 is negative 8. So your fraction is negative 1/8. Another one more.
Wait, 1 times the numerator and 1 times the whole fraction.
Yeah, it's 1 times the whole fraction for that. Okay. Now, when we go to simplify this one, I'm not evaluating. Notice it just says simplify. Please, guys, remember that you only relocate the one that has the negative exponent. That 3 has an understood positive 1 as an exponent, so he stays exactly where it belongs. The only thing that gets to be relocated is that y. He gets shot down to the bottom. The 3 remains on top, and it's 3 over y squared. That's the simplified form. For b, that negative 4 is telling you you are a negative 4, not that you have a negative exponent. That is negative 4. That negative 4 remains on top, and this guy needs to be relocated up to the top because he has a negative exponent. A negative exponent says, I'm a fraction, but I'm in the wrong place of the fraction bar. So because it's k to the negative 4, that... So if we were to look at the next types of questions, let's look at this one. If I ask you to simplify these, what you're going to do is you're going to relocate those that have negative exponents and simplify anything to the power of 0 to become 1. So this one looks as following. Immediately when I see a to the 0, I know that's going to equal the value of 1, correct? So this is equal to 1. And 1 times y to the 5 is just y to the 5. And the y has a positive exponent. So Mr. Y, you're good where you are. The x, however, that's on top, has a negative exponent. I am going to need to relocate him to the bottom bunk to make it positive. Now, I have to put something on top so that I appear to be a fraction. It's 1 over. So the entire expression is now 1 over x cubed y fifth. And in practice that you guys are going to complete, basically follow the following. Remember that when multiplying variables, we add the exponents if it's the same base. If I have this guy here, I'm doing 2 times 2, which is 4. And then imagine you have 2 m's being multiplied there, and you're multiplying them by 3 additional m's. So altogether, you really have 5. That's where the rule, when multiplying variables, like a to the n times a to the m, you add their exponents. And when you're raising a power to a power, you multiply. So let me give you an example of that as well. Okay?
That's the one.
So if I skip down to this question, number 12, what you're doing is you're distributing the exponent to everything inside. But remember that you are raising a power to an additional power. And when you do that, you multiply the exponents. Power to power, multiply. The 2 has an understood 1 as an exponent. So when you distribute that negative 4, you're going to get 2 to the power of negative 4. And then you're going to distribute this negative 4 to the 2, and you get x to the power of negative 8. Then you look at it and go, oh no, they're both negative exponents. I need to relocate them. And so it means you're going to have a fraction. And this guy gets shot down, 2 to the 4. This guy gets shot down, x to the positive 8 with a 1. And that simplifies to 1 over 16x to the 8. So I'm going to skip on to the next page. For this example, way number 1, if you use the commutative property of multiplication, you know you're multiplying all these together. So it's really m to the 4 times 2 times m to the negative 3. When multiplying variables with the same base, you add their exponents. So when you have these guys and you sit them next to each other, you can add those two numbers and you get m to the 1, and the 2 just gets rewritten. That's way number 1. Way number 2 would be to actually rewrite the negative exponent so that it gets relocated down to the bottom. Then when you multiply, remember, you have 4 m's on top being multiplied by 2 with 3 m's on the bottom. Anything over itself divides away, so this divides away with this divides away with this divides away with this, and you're left with only 1 m on top, which leads you to 2 times m, which is the same answer. Show you another one of your independent practice. I want to show you number 22. Yeah. So when I'm simplifying this, what happens is that this poor little x comes down to the bottom, but because he gets shot down to the bottom, the 1 that's the coefficient in front remains. That's the reason why we always have a 1 on top. The 4 has an exponent of 1, it's positive, it remains. The x has an exponent of positive 4, so it remains. And when I bring that x to the 1 down here, I can now simplify x to the 4 times x to the 1. And so I get the 4. And if you think about what this really is, before you use the shortcut, that's 4 x's, that's 1, altogether that's 5. So that's where the rule comes from, that when you're multiplying variables with the same base, you just add their exponents. And then as a quick little review of the reason to why power to power is multiply, think of it this way. If I have x to the power of 5 raised to the power of 3, that means I have 3 sets of x5s. So that's really like x to the 5 times x to the 5 times x to the 5, which I expanded out. I would have x times itself 5 times. Okay, so then I would have 3 sets of these, which is really a total of 15. So instead of having to write out all of that every time, mathematicians said, hey, don't worry about writing it out like, oh, there's 3 sets of x to the 5s, and each x to the 5 is 5 of them, and that gives you altogether 15. They said, don't worry, when you're raising a power to a power, you multiply. 5 times 3 is 15. So this is different than x to the 5 times x to the 3, because that you add the exponents, because you get x to the 8. Yes?